Hello and welcome to the course of manufacturing method. Now in this course, we have come to the to most of the most we have come to an end of this subject. So this is the last chapter we are dealing with right now. So in this chapter we will be seeing about the conventional machining, and this is the introduction of the conventional machining process. So let's start our lecture with lecture objective. Here in this lecture, the lecture objective is to get an insight about the unconventional machining processes. So we will know about this unconventional machining processes, and we know about the advantage and disadvantage of these unconventional machining processes. We know about the classification of the unconventional machining processes, and we know about the process parameter and economy of the processes. So that is what we will be dealing in this lecture. So this is an introductory lecture about the unconventional machining, and from the next class or from the next lecture we will be seeing the detail of these processes. So let's start our lecture. So first, what is conventional machining process? So we have already discussed this, that metal, whenever the metal is removed by the means of the tool which is harder than the workpiece, and the both of them are in contact with each other, in that case, so what is the definition of the conventional machining that we have discussed earlier? That is, machining is nothing but a process of material removing in the form of chip by using a wedge shaped tool. That tool is called cutting tool, in a machine, in a device called machine tool. That is the definition of the machining. So that is conventional machining. So what is important in case of conventional machining? Chip formation, that is important. The cutting tool is important. The contact between cutting tool and the workpiece, that is also important. And the work will occur in a machine tool, that is also important. So whenever these four categories will be satisfied, at that time what we will say? We will say that the process is conventional machining process. Now what are the demerits? Why this conventional? Why the need of unconventional machining will rise? Because there is some demerits of the conventional machining processes. So what are those? The disposal, there is huge amount of chip formation, and that disposal and recycling of this chip are very difficult and very tedious process. Okay, so disposal of and the recycling of the chip is very difficult and tedious process. So that's why we need to think about other processes. We need to think about the other processes, so that this chip formation won't be there. First, next, the power requirement or power consumption, because there is contact with the workpiece, and there is contact between workpiece and the cutting tool. As there is contact between workpiece and the cutting tool, there is huge loss, huge frictional loss of power. That large cut, and that's why large cutting force will be required, and that large cutting force are involved in this process. That large cutting force will require larger power. That means the power consumption is another issue. So there is two issues due to which we have to think about the other processing methods. So those other processing methods are unconventional machining. So see, in unconventional machining process, there are two type of unconventional manufacturing process. First one is unconventional machining, next is unconventional forming process. So in case of unconventional machining, harder and difficult to machine material can easily machined. So this is the first thing, that harder or difficult to machine material. That means for machining, the indentation is important, but that indentation, whenever there is indentation, that indentation is only possible if the indenter is harder than the workpiece material. So the indenter should be harder. So the hardest material, say if we have to machine boron carbide or diamond, at that time what will occur? At that time, this material or any hard material, such as, say for example, austenitic steel, so this type of the materials, these are hard to machine material. So those hard to machine material can be machined very easily using this unconventional machining process. And this unconventional machining process, there is no contact between the cutting tool and the workpiece, or very nominal contact. So tool wear is very nominal. Tool wear means the wearing out of the tool, or the tool wear, detailed discussion of the tool wear we have done in the tool wear lecture section. So the for the need is first to for easy machining of the hard to machine workpiece first. Secondly, for minimizing the material for maximizing the MRR, and minimizing our tool wear, and there is very low amount of chip formation, because for maximum of the unconventional machining process are chipless process. That means there is direct evaporation, there is no chip is formed. So this is the process of unconventional machining process. So what are the classification? So the classification of the unconventional machining processes are: first, the unconventional machining process classification can be done based on the type of the energy required to shape the material. First, on the basis of type of the energy. So on the basis of the type of the energy, first is thermal energy method, where we use the thermal energy to remove the material, or mainly to evaporate the material directly, so to get the desired shape. That is our thermal energy method, firstly. Secondly, that is the example of thermal energy method. There is various example of the thermal energy method, such as laser beam machining, electron beam machining, etc. Next is electrical energy method. Electrical energy method means electrical energy is in electrical energy method, what is done, the electrical energy is used to evaporate or to melt the material, so that it is directly evaporate, so that we can get the desired shape. That electrical energy method is known as the electrical energy method. Example of the electrical energy method is plasma arc cutting or plasma arc machining. Okay, now electrochemical energy method. In electrochemical energy method, the concept of electrolysis, came into action, and that concept of the electrolysis would give us the chemical, electrochemically remove the material, that is known as electrochemical method. Next is chemical energy method. In case of explosive machining, in case of chemical grinding, so these are the process where we use chemical reaction to remove the material, that is chemical energy method. And mechanical energy method, where the mechanical energy, or mainly the vibration energy, is used to remove the material. So this is the process example of this mechanical energy methods is ultrasonic machining process. So these are our basic type of classification according to the energy required for to shape the material. So these are the basic types. Next, the based on the mechanisms that involved. So based on mechanism involved, the erosion, ionic dissolution, and vaporization are the type of the mechanism in which involving those the material is removed. Erosion means, what is erosion? Erosion means very slow wearing. That means when erosion occurs, if you take any sharp object and just continuously put that sharp object in any place, that your in any workpiece, that your workpiece whatever the hardness of that workpiece, if you continuously indent, or if you continuously poke that workpiece, some of the material, some of the very small amount of material will be wear out from the workpiece surface, and is known as that is the main case of erosion. Erosion means very slow wearing out due to anything. Erosion may be chemical erosion, can be seen, maybe there is mechanical erosion due to vibration, maybe electrical erosion. But erosion, what is erosion process? Erosion means very slow wearing out. Okay, slow wearing out from the inside, that is known as erosion. Next is ionic dissolution. Ionic dissolution, where we can see for electrochemical thing, we can see. So for electrolysis, what we can say, that in electrolysis there is one anode and one cathode. In from cathode to anode, the ion transfer will occur. This ion transfer is known as ionic dissolution. Next is vaporization, due to thermal effect, due to electrical effect, due to chemical effect, that means due to exothermal reaction. What can be seen, that in the workpiece the material will be evaporated directly. This process means the material will be melted and evaporated. This melting and evaporation process is known as complete vaporization process. So material is removed in the form of vapor in case of vaporization. So these are the classification based on mechanism. Now another type of the classification can be done based on the energy, source of energy required for material removal. So see the difference very carefully, because here, see here what we are according here, the classification is according to the type of energy required to shape the material. Now here, the source of energy required for material removal. So whenever the material removed, that material removed is whenever that material is removed by the fluid pressure, then is the process is known as hydrostatic pressure pressure machining. Next, if there is the material is removed by high current density, at that time the process is known as uh, our high current density process. Next, similarly, high voltage and ionized material. These are the type of the energy that is required to remove the material. So now next, based on the medium of transfer of energy, how the energy is transferred, on based on that, high voltage particles, electrolyte, electron and hot gases are the type of the unconventional machining processes. Now we need to consider some point for correct selection of the correct selection of the unconventional machining process. So for correct selection of the unconventional machining process, first we need to know about the physical parameters. So those physical parameters which we require, means our desired final shape should be known to us. Our desired physical parameters should be known to us. Next, the shape to be machined, which shape to be machined, that should be known to us. And process capability and machining characteristics, this process capability, machining characteristics and economic consideration, these are the things that we should know for selection of the unconventional machining process, because this is very important, because there is numerous number of unconventional machining process, and nowadays you can see that there is hybridization between this unconventional machining process. So hybridization means two or three unconventional machining process are clubbed together to get better and better results. So as the demand is getting high, we need to know the the particular selection for the particular operation. So that particular selection, that process selection will be based on four parameters, based on four pillars. I say that pillars are first, that is physical parameters. Secondly, shape of the shape that are to be machined, process capability or machining characteristics, and some economic consideration. So see here, the what are the physical parameters? Here ECM, EDM, EBM, LBM, PAM, USM and AZM. What are the full forms? ECM means electrochemical machining. ECM, electrochemical machining. EDM, electro discharge machining. EBM, electron beam welding. LBM, laser beam machining. Sorry, EBM, electron beam machining. LBM, laser beam machining. PEM, plasma arc machining. USM, ultrasonic machining. And AJM, that is abrasive jet machining. So here see the potential or the voltage. So as per the voltage available, that as per the voltage available, we can select the process that is available. So the potential or voltage for ECM is 5 to 30 volt, EDM is 50 to 500 volt, EBM is 200 to the power 10, 200 into 10 to the power 3 volt, and LBM is 4.5 into 10 to the power 3 volt. Plasma arc machining 250, ultrasonic 220, and abrasive water jet machining is 220. So next is current. Electrochemical machining, the high current operation, that is 40,000 ampere current is required. For EDM 15 to 500 ampere current will be required. For EBM the current requirement is very low, that is 0.001 ampere. For LBM it's 2 ampere. For plasma arc machining it's 600 ampere, and for ultrasonic machining it's 12 ampere, and abrasive jet machining is 1 ampere. The detail of these machining processes will be discussed in the later lectures. So now that one idea will be given, that idea, this is the idea for physical parameters. Similarly, the ideas for three other pillars that I have mentioned just a while ago, that idea should be given to you. So now the power requirement for electrochemical machining is 100 kilowatt. For EDM it's 2.7 kilowatt. See, very low power requirement. Next, for EBM it is 0.15 kilowatt, and for LBM 20 kilowatt. Plasma arc machining it's 220 kilowatt. For USM or ultrasonic machining is 2.4 kilowatt, and for abrasive jet machining it's 0.22 kilowatt. And the gap, that means the gap between the this gap means the gap between the workpiece and the electrode and the and our tool. So that gap between the tool and workpiece in case of electrochemical machining can be 0.5 mm. For EDM the gap is 0.05 mm. For electron beam machining the gap can be 1000 mm. For laser beam machining gap can be 150 mm. For plasma arc machining this gap can be 7.5 mm. The for ultrasonic machining this gap can be 0.25 mm, and for abrasive jet machining this gap can be 0.75 mm. The medium for electrochemical machining, the medium will be electrolyte. For electro discharge machining the medium is dielectric fluid. EBM, for EBM the medium will be vacuum. For laser beam machining medium will be air. For plasma arc machining the medium will be argon, hydrogen or nitrogen. And for ultrasonic machining the medium will be abrasive grains and water. For abrasive jet machining the medium will be nitrogen or carbon dioxide or air. And the work material for ECM, for electrochemical machining, difficult to machine, any difficult to machine material can be machined by using ECM. For EDM, tungsten carbide and electrically conductive material can be machined. Only electrically conductive material can be machined by electro-discharge machining. EBM and LBM can process any material, any feasible material in nature can be machined by EBM and LBM. And plasma arc machining, all the material which conduct electricity can be done by plasma arc machining. And ultrasonic machining can machine tungsten carbide, glass, quartz. So this type of the hard to machine and brittle material can be machined by ultrasonic machining process. And abrasive jet machining can be done for machining of hard and brittle material. So for the machining of hard and brittle material can be done by using uh, hard and brittle materials can be done by using abrasive jet machining process. So these are the physical parameters. Now similarly we have to see about the shape. Those shapes can be machined by and according to that shape we can see in this table, we can see that what are the machining process that is suited. For example, for micro holes, LBM is best suited for producing small holes. EBM will be suited for deep holes. ECM will be suited for shallow hole. USM and EDM will be suited for precision through the cavities in the workpiece. USM and EDM for honing. ECM is suited for etching small portion. ECM, EDM for grinding. AJM, EDM will be suited. Deburring for threading, for cleaning rapid cuts profile, and for shallow pocketing. The suited mechanism, suited machining process has been shown in this table. Now the process capability means the output that can be achieved by the by all of this process can be seen here. Say for LVM the MRR is 0.1 millimeter cube per second. The surface finish can be found as 0.4 to 0.6 CLA, that is cumulative average. And accuracy can be found up for 25, and specific power requirement is 2700, that is power density is 2700. So these are all the process capabilities. These are seen in this in this table. Now the process economy analysis is also shown here. So depending upon these four criteria, all the process selection can be done. Now what are the advantage of the UCM or unconventional machining process? Unconventional machining process increases the productivity, it reduces the number of rejected component. The closed tolerance, that means closed dimensional tolerance can be possible. Tool material needed need not to be harder than the workpiece, and the machine surface does not have any residual stress because there is no contact between the workpiece and the cutting tool. And the process limitations are the cost is very high and MRR is low. So these are the limitation and advantage of this process. So thank you, hope you enjoy this lecture, and if you have any problem you may ask in the live class. Thank you.